Welcome back to our lecture series in rate processes. So, today we will take up this topic on kinetics of some specific reactions, and under this heading we will talk about enzyme inhibition. Till now we have talked about reaction rates, rate laws, effect of temperature on reaction rate, then complex reactions. We also have talked about theories of reaction rate, then we talked about kinetics of some specific reactions, and under this heading we will deal with this enzyme inhibition. We already have talked about enzyme kinetics, that is the biocatalysis where enzyme is the biocatalyst. Okay, like chemical reactions, normal chemical reactions in the biochemical system, these enzymes are acting as catalyst. So, under this heading enzyme inhibition, we will talk about what is meant by enzyme inhibition and various aspects of this. Okay. Now, before going into the details of it, let us have some recapitulation. Now, we have dealt with this Michaelis-Menten kinetics, where we talked about this Km, that is Michaelis constant. Now, if this Michaelis-Menten equation is written, in this form, that is in this form means 1 by V is equal to Km by V max into 1 by S, where S is substrate concentration, plus 1 by V max. So, this is M, this is X, and this is C. Okay, and this is Y. Now, Km is a constant. So, this is called the Michaelis constant. Now, small Km means tight binding, that is binding interaction is tighter. So, like suppose you have got this is your enzyme and say this is your substrate. So, they are bound tight together. Okay. So, it is difficult to separate them out maybe. Okay. So, when Km is small, then this is more, this interaction is more, that is binding is tighter, and high Km means weak binding. Okay. So, when Km, that is Michaelis constant, is high, then binding interaction is weak. Now, this is useful, I mean this Km is very useful to enzyme these various reactants, and they are how efficient some enzyme is with respect to some reactant or with respect to a different reactant. Now, so for example, if we think of this hexokinase, this enzyme, now when the substrate is D-fructose, it is 1.5 millimolar, Km is 1.5 millimolar, whereas for D-glucose it is 0.15 millimolar. So, the value of this, I mean this for D-glucose is value of Km for D-glucose is less, that means here it is tight binding. Okay. It is also useful to compare Km for a common substrate used by several enzymes like hexokinase and glucokinase. For hexokinase D-glucose case, it is 0.15 millimolar, whereas for glucokinase D-glucose it is 20 millimolar. Okay, so this value is higher, okay, compared to this value. Okay, so we can compare, compare whether the binding is stronger or the binding is weaker. Now, enzyme inhibition. Now, enzyme inhibitors are important for a variety of reasons. Now, it can be used to get information about the shape of the enzyme active site. You have got, suppose you have got an enzyme like this, it is basically a protein, and say this is your active site. Okay. So, this active site, in this active site, suppose your reactant fits, and then chemical reaction takes place, and after that your product is formed, plus your enzyme is written back. Okay. So, inhibitors are used to find information about the shape of the enzyme active site, say this site maybe, and the residues in the active site. So, there are residues in these active sites. So, maybe in this region, in this region, this is the active site. So, residues are there. So, which residues are there and which residues are important compared to the other, that we can get information about. Then it can be used to get information about the mechanism. Okay. So, to get the information of the mechanism or how this reaction is taking place. So, mechanistic part is also, we can find out the information of that. It can be used to get information about the regulation or control of metabolic pathways. So, using various inhibitors, we can find out these things. And also for drug design, these studies are very important, that is, enzyme inhibition studies are very important. Next, types of inhibition. One is called, when it is the question of inhibition, that means we need an inhibitor. Okay. So, reversible inhibitor is basically a substance that binds to an enzyme to inhibit the reaction, but can be released in a reversible fashion. So, usually involves formation of non-covalent bonds, maybe some van der Waals interaction, maybe hydrophobic interaction, or maybe some electrostatic interaction. So, these are the three non-covalent modes of interaction by which this inhibitor can bind with the enzyme. Next is irreversible inhibitor. What is an irreversible inhibitor? It is a substance that causes inhibition that cannot be reversed. So, it is a reversible formation of bond, that is, usually it involves the formation or breaking of covalent bonds. Okay. That is, breaking of covalent bonds maybe within enzyme or maybe formation of new bonds. That is, it is basically a chemical transformation of your enzyme. So, therefore, the enzyme loses its activity and it is an irreversible fashion. Okay. But for reversible case, since the binding is not a covalent interaction, bond is not a covalent bond, so maybe it can be reversed back. Okay. So, because like hydrophobic, hydrogen bonding, maybe electrostatic or van der Waals interaction, these are the modes of interaction for reversible inhibition. Okay. Now, so when you talk about irreversible or reversible inhibition, there are other things that we should take into account. One is, there are three types of broad classification with respect to inhibition. One is competitive inhibition, next is mixed or non-competitive inhibition, third is uncompetitive inhibition. Okay. So, competitive inhibition, mixed or non-competitive inhibition, and the third one is uncompetitive. So, competitive, non-competitive, uncompetitive. Okay. So, these are the three types of inhibitors. Okay. So, maybe you can call like competitive inhibitor, maybe in another case you can call non-competitive inhibitor, or maybe uncompetitive inhibitor. So, let us look into the chemical scheme for enzyme inhibition. See, in this particular scheme, enzyme plus substrate producing enzyme substrate complex, then it produces the outcome, that is your product, with a rate constant of Kb. This is K is the forward rate constant for ES formation, and this is the backward rate constant, the dissociation of ES complex. The moment you add some inhibitor, what is going to happen? that maybe this inhibitor directly binds to the enzyme, okay, producing enzyme inhibitor complex like this, okay, EI giving rise to E plus I and back to EI. So this is one reaction. So this is KI, okay, and this is for your inhibitor dissociation process, okay, or maybe the reverse process is enzyme inhibitor complex formation, and the forward process is enzyme inhibitor dissociation. Okay, you can think in other way also. You can write this reaction in a reverse fashion. Another situation is enzyme substrate, then it binds to inhibitor producing enzyme substrate inhibitor, then it gives you in a reversible fashion enzyme substrate plus inhibitor. So the corresponding equilibrium constant can be written as this. Okay, we are defining one quantity alpha, which is 1 plus I by Ki, or alpha primed is 1 plus I by Ki primed. Okay, and in this case V can be written in this fashion, and if we plot in this way 1 by V versus 1 by S, then we see that there are 3 situations, okay, when alpha is greater than 1 and alpha prime is equal to 1, okay. For this one we are getting alpha is equal to alpha prime is equal to 1. This is another situation. The second situation is alpha is equal to 1, alpha prime is greater than 1. The second means this one in second for the curve B, and here you see that alpha is equal to alpha prime is equal to 1. So this may be another situation. Third situation is that like this, and you see that difference is that you see that for this one the intercept same for both curves. We see that these two intercepts are different, and also it is cutting the one by S axis at different points. Here also they are cutting at different points. Here we see that these intercepts are different, but they are cutting at the same 1 by S axis. So how this is coming we will be discussing later on. So these 3 situations may be considered. Okay. Irreversible inhibition, the inhibitor binds with the essential part of the enzyme active center by covalent bond, resulting in loss of activity. For example, so this schematically written in this way, that say this is one reactant, this is your enzyme E, so it is producing something like this, and HX something else also, another resulting substance is produced, but you see that this is a covalent bond formation. So that means enzyme activity, since this is a permanent bond formation, so enzyme is no longer free, okay, enzyme is no longer free to react with another substrate. So the reaction after this reaction happens, no further reaction is taking place, okay. So that means the enzyme loses its activity. So this is called irreversible inhibition. It is not in a reversible fashion. So backward reaction is impossible, or even if it happens to an infinitesimally small extent, so that is practically not of any significance. Okay. So this is basically a schematic representation of irreversible inhibition. Okay. Now inhibition pattern, an inhibitor may bind at the same site as substrates, okay. That means suppose you have got this enzyme, say this is your your substrate, and say this is another similar looking inhibitor. Okay. They have got resemblance in their structure. So, maybe what is happening that it will come over here, that is it will compete with this. So, this one also this one, these two are having the probability of binding to this or occupying this space. Okay. So they are structurally similar, so they are having structural resemblance, and as a result of which they will bind to the same active site. Okay. Next situation is an inhibitor may bind at a different site and thereby altering the catalytic activity, although substrate binding remains identical. So, suppose your enzyme is this and your inhibitor binds at some other place, okay, in such a way that suppose here it binds your inhibitor and it modifies your active site or active site activity, okay, in an indirect fashion, so that reaction gets slowed down. Okay. Although apparently this particular site, that is active site, is not disturbed, but because of this binding some internal structural change may happen, as a result of which this enzyme activity may get reduced. Okay. The third situation is that many inhibitors may do both of these, that at the same time it may bind here, also bind at a different place. So, they are doing in a parallel fashion maybe. As I told you that the type of inhibitors, I mean inhibition, is competitive, non-competitive or mixed, and the third one is uncompetitive. Okay. So, competitive inhibitor, it competes with the substrate. Okay. Suppose you have got similar kind of substrate and inhibitor, then what is happening, that enzyme does not know which one, whether this one is its right substrate or this one is its right substrate, but to us this S is our right substrate. So, what is happening, that it becomes difficult, since they are having structural resemblance, it is difficult for the enzyme to discriminate between these two, and as a result of which it is said that these two compete for the same active site. Okay. Malonate is a competitive inhibitor of succinate for succinate dehydrogenase, like the scheme shown over here. Okay. Although succinate, for succinate, after adding succinate or in presence of succinate dehydrogenase, it produces fumarate, but here no reaction occurs, but they are having some structural resemblance because it is a diacid. This is also diacid, although it is only one CH2 spacer, there are two CH2 spacers. Okay. So, for the formation of a double bond you need another C, since it is not available over here, so no reaction occurs, but although they are having structural resemblance, so they are competing competing for the same enzyme, that is succinate dehydrogenase. Okay. Next, competitive inhibition. The scheme is like the classical scheme. This is the normal scheme: enzyme, substrate, enzyme substrate complex, then enzyme back, then product. Okay. Now, since the inhibitor is present there along with your substrate, what is happening? Now, this inhibitor again binds with your enzyme. So, what will happen with a binding constant Ki, okay, producing Ei. So, a competitive inhibitor lowers the amount of unbound enzyme available to substrate binding, and as a result of which Km per substrate increases. Okay? Km per substrate increases means your binding is less, as I told at the very beginning. Okay? Now, what will happen? The other situation is that if you add your substrate to a huge extent means that the substrate concentration is very high, then what will happen, that concentration, if we take the concentration ratio of substrate to inhibitor, then the ratio for substrate to substrate is more, I mean more amount of substrate is there. Okay. So, what is happening, that maybe almost all the enzyme molecules are are surrounded by many substrate molecules compared to I inhibitor. So, what is happening? So, probability of binding of the substrate molecule increases since you increase the concentration of your substrate. Okay? So that this path is more accessible than this path. So, this is happening parallelly, but since the concentration of your substrate is very high, therefore, this is the major channel. So, competitive inhibition can be minimized with high substrate concentration. It cannot be eliminated, but it can be minimized, that is, the effect can be minimized with high substrate concentration. Okay? So, what is happening for your competitive inhibition? A competitive inhibitor lowers the amount of unbound enzyme available to substrate binding, and thereby Km for substrate increases. And if we increase the concentration of your substrate, then competitive inhibition remains, but the effect is minimized. The effect is minimized because more of substrates are there. So, probability that the substrate will bind to enzyme is more, as a result of which your normal reaction path is more promoted compared to this inhibition path. Okay. Next, so the corresponding plot 1 by V versus 1 by S, you see that this is for your no inhibitor present, and this is for your competitive inhibitor present. Okay. Let us go back to the earlier slide. Okay. This one, you see, here you see that this is 1 by V axis, intercept for both red and blue curve same, but corresponding meeting point at on this 1 by S axis, you see the intercept on x axis, it is 1 by Km, okay, minus 1 by Km. You see this is nearer to this point and this is farther. Okay. So, an intercept is 1 by V max. So, maximal velocity remains same, okay, and the slope you see Km by V max. So, V max 1 by V max same for both. So, Km is different. Okay. So, Michaelis constant is different. Okay. So, for your competitive inhibition, if it is a case of competitive inhibition, you will be getting a curve, I mean a plot like this, in absence of inhibitor and in presence of an inhibitor. Okay. So, this type of plot you may expect for a competitive inhibition. As I told you in the here also, you see. So, this is a case of competitive inhibition. So, three possibilities are there. Okay. So, first possibility we have just explored. Okay. So, pictorially competitive inhibition for a unimolecular reaction, enzyme, substrate, enzyme substrate complex, then product. Okay. Then product will be released and enzyme will be freed to come back to here and do this in a cyclic fashion. Okay. So, in presence of a competitive inhibitor, what is happening, that your enzyme is here, they look very similar. You see this part and this part, they look very similar, although this side is different. It is pictorially demonstrated in this way. You see that this one is having the option to bind here, take this place, or maybe this one can attach over here. Okay. So, what is happening, that if it attaches, then substrate cannot access this pocket for the reaction to take place. So, basically enzyme competitive inhibitor complex. So, now what you can do is you can increase the concentration of this substrate. So, probability wise, if it is very high, then competitive inhibitor cannot compete concentration wise, and as a result of which more of substrate will bind to enzyme to give rise to product. So, that thereby you can minimize. So, it is a unimolecular case, that one pocket, one substance. Now, if it is a case of two pocket and two substance, then you see this is your substrate and this is another substrate. Okay. So, you see that substrate 1, substrate 2, it is producing enzyme substrate complex, then giving rise to products. Now, if you have your competitive inhibitor over here, so which will compete with this S, then in place of S, this competitive inhibitor will take this place, so that to have this further reaction, since inhibitor is here, so further reaction basically cannot take place. Okay. So, these are basically pictorial representation. So, the pictorial representation of the enzyme pocket. Okay. Next is uncompetitive inhibition. Okay. What is that uncompetitive inhibition? That your uncompetitive inhibitor binds to the enzyme substrate complex. Okay. It does not bind to your enzyme. Okay. So, what happens is that once enzyme substrate complex is formed, then this has got two options. Either it will go this way to produce your product, or it will move this way to give rise to enzyme inhibitor substrate complex, or sometimes it is called as ESI or EIS. Okay. So, what happens? The decrease in Vmax and Km. Okay. Now, you see, if you increase the substrate concentration, suppose there was 1S initially, now you increase it to 6, 1, 2, 3, 4, 5, 6. So, what will happen, that if you increase this substrate concentration, more of ES will be formed, and the more this is formed, that is enzyme substrate complex is formed, it has got more option to move to this pathway. So, that means you cannot minimize this step, because in no way you can stop this process, because this process is very much dependent on the availability of ES. Okay. So, therefore, the effect of this uncompetitive inhibition cannot be minimized with high substrate concentration. Okay. So, if you go back to competitive inhibition, you see that here the inhibitor binds directly with enzyme, but in case of uncompetitive, it does in a different fashion, that it binds with enzyme substrate, okay, to produce enzyme substrate inhibitor, a different complex, and once it is formed, it cannot give rise to this one, that is your product. okay, and there is a change in Vmax as well as Km. Okay. So, uncompetitive inhibition, you see substrate, this is another substrate, this is the third substrate. So, what is happening? These three are binding with the enzyme to produce, to give rise to product P. This is a product, then P2 and also something over here. So, in presence of uncompetitive inhibitor, so your substrate binds, okay, giving rise to enzyme substrate, and then uncompetitive inhibitor binds over here. Once it binds, then this S2 cannot access this site. So, reaction stops over here. Okay, you see that this uncompetitive inhibitor binds with enzyme substrate complex, not with the free enzyme. Okay, its action is important when substrate is bound, already bound with the enzyme. Okay, so when substrate is not present, its action is it is not discernible. You cannot see its action. But the moment substrate is present, it binds, it stops the enzyme activity. Okay, it stops the enzyme activity. Okay, this is uncompetitive. You see, for uncompetitive, this inhibitor increases, okay, and the corresponding plots, you see that this these numbers, this intercept on y axis, it is changing, okay, and also this intercept is changing. Okay. So, both V and also Vmax and also Michaelis constant, these are changing for an uncompetitive situation. Okay. So, for your competitive, you see it is one point on your y axis and two different points on your x axis. You see here 3 different points on y, 3 different points on x axis, of course in negative fashion. So, this is uncompetitive situation. Okay. Next, mixed or non-competitive inhibition. Now, the situation is the inhibitor may bind to both free enzyme as also the enzyme substrate complex. The affinity of the inhibitor to the two complexes could be different. Okay. If binding of inhibitor results in a change of affinity for the substrate, Km will be changed, and as a result and the name is mixed inhibition. Okay, if Km is changed, but if only Vmax is affected, then it is called non-competitive inhibition. Okay, so two situations: mixed inhibition, Km will be changed; non-competitive inhibition, Vmax will be affected. The scheme is, kinetic scheme is this: enzyme, substrate, producing enzyme substrate complex, giving rise to your enzyme back and product. Now, this enzyme can bind to both, I mean this Es as also E, with Ki for E and Ki primed for Es. So, giving rise to Ei for here and enzyme inhibitor substrate complex for here. Okay. But remember, for your uncompetitive, the situation is like EIS. So, only the enzyme binds over here with enzyme substrate, but not with your enzyme. But here, non-competitive or mixed fashion, you see that enzyme binds with Es and your inhibitor binds with Es and E with different rate constants, equilibrium constants, EIS and EI. Okay. So, if Km is changed, it is called mixed. If only Vmax is affected, it is called non-competitive inhibitor. Okay. You see mixed inhibition, substrate, okay, enzyme, this is another substrate. Okay. So, it is basically a bimolecular scheme. Okay. So, substrate binds with enzyme producing enzyme substrate, another S2 also binds over here, giving rise to your product. Okay. You see, this is a case of mixed inhibition, I mean non-competitive or mixed inhibition. You see non-competitive inhibitor, substrate, substrate 2. First substrate binds, then in presence of non-competitive inhibitor this is produced. Or in another situation, your enzyme first non-competitive inhibitor binds, then in presence of your substrate it gives rise to this. Okay. So, basically this enzyme, free enzyme and enzyme substrate inhibitor, they are in equilibrium via these two maybe intermediates. So, these four are in equilibrium. Okay. So, that is why basically you can put you know basically enzyme inhibitor, then enzyme inhibitor substrate, just put one substrate over here, so that these four are in equilibrium. Okay. And only enzyme substrate channel can give rise to this enzyme plus product. So, probability wise free enzyme substrate is reduced and reaction rate is lowered. Okay. So, it is called the mixed inhibition. Okay. So, so this is the scheme: enzyme substrate, then giving rise to, I mean enzyme plus substrate giving rise to enzyme substrate, then product plus enzyme. In presence of inhibitor, what is happening? Enzyme inhibitor substrate, then this is in equilibrium with enzyme inhibitor, then enzyme inhibitor is equilibrium with this one. So, this is the equilibrium scheme, you see, as I have shown over here. This is the equilibrium. These four species are in equilibrium. Now, what is happening that if you put, so you see here there is one channel through which you can get your product. Okay. So, if you increase your substrate concentration to a huge value, huge number, then what is happening, that possibility of this step, I mean this channel is a little increased, although these steps are there. So, you can partially overcome the effect of this inhibition, mixed inhibition, by increasing your substrate concentration. So, what is happening, as a result of which what is happening, you see that Vmax is decreased and Km may get increased or may get decreased. Okay, you see these are three situations, you see this is increased, inhibitor is increased, you see, and this cutting point is here in between, not on your y axis. So, three distinct situations are there. This is your mixed or non-competitive. Come back to earlier slide. Okay, that this is one case, this is the third case, this is the second case. Uncompetitive, this is the non-competitive or mixed inhibition. Okay. So, for your mixed inhibition, like your competitive inhibition, is a kind of competitive, but not exactly competitive. It is a non-competitive, but it has resemblance to your to competitive, that you can partially overcome, although competitive inhibition can be greatly overcome with high substrate concentration. Here also you cannot fully overcome, but you can partly overcome with high substrate concentration. So, this is a typical plot for your mixed inhibition. Okay. So, general non-competitive inhibition, you see no inhibitor present, this one. Non-competitive inhibitor, you see it is here. Okay. Km is remaining same. Okay. Km is remaining same. So, Km is remaining same means, you see, this is a non-competitive inhibition. If Km is affected, it is called mixed inhibition. Okay. You see here Km is affected, Km is affected. Okay. So, here Km is not affected. So, it is called your non-competitive inhibition. Okay. So, if this cutting point is somewhere over here, then Km will be affected, but if this cutting point is here, then Km is not affected. You see only Vmax is affected, you see 1 by Vmax over here, there is another one, I mean this is a different 1 by Vmax. So, Vmax is affected. So, that is why it is a non-competitive inhibitor. Okay. Again go back to competitive inhibition, you see the typical plot for competitive inhibition. Okay. This one you see Km is changing, but Vmax is remaining same. Okay. And non-competitive Km is fixed, Vmax is changed. Okay. And this is because your scheme has changed. Okay. Scheme means the reaction scheme has changed, and as a result of which your the plot is different. Okay. So, let us go back to this slide. This is your non-competitive inhibition, this is your competitive inhibition, this is uncompetitive inhibition. Okay. So, thus we can explain these three curves arising out of using enzyme kinetics when you talk about enzyme inhibitors, and three broad classifications are there: competitive, uncompetitive and non-competitive, that is competitive, uncompetitive and non-competitive. Okay. So, for your competitive inhibition, Vmax is not changed, only Km. As I told you, Km is Km is increased, and Km is increased means your binding is less, binding affinity is less as a result of the presence of your inhibitor. Okay. For your uncompetitive, it is a different situation, that you get two parallel plots, as if these two are occurring in an unconnected fashion, and the third one has got connection over here. You see that Km is not changed, but Vmax, okay, Vmax is changing. Okay. So, now why have we learned this enzyme inhibitors? What is the necessity of exploring this one? Now, many drugs are enzyme inhibitors. Okay. Enzyme inhibitors means sometimes you need to inhibit the action of some of the enzymes within our body for some for some reason, or in some cases, suppose in presence of some inhibitor, some physiological process are impaired. Okay. So, in that case you need to remove your inhibitor. Now, many drugs are enzyme inhibitors, so their discovery and improvement is an active area of research in biochemistry and also in pharmacology. A medicinal enzyme inhibitor is often judged by its specificity and its potency. Okay. Now, by its specificity and potency means, specificity means how specific its action is, and a high specificity and potency ensure that a drug will have few side effects and thus it will have low toxicity. Toxicity means side effects. Suppose we are putting a drug, we are giving a drug which has got side effects, means it is parallelly affecting other biochemical channels. Okay. It is affecting our interested, I mean the channel which we are interested in, along with other channels which is not desirable. Okay. So, we need to minimize the side effect and we need to minimize the toxicity. Okay. So, that is why high specificity and potency is very important. Okay. Now, enzyme inhibitors also occur naturally and are involved in regulation of metabolism, and natural enzyme inhibitors can also be poisons, okay, and are used to defend predators or as ways of killing prey. Okay. So, therefore, natural enzymes are also very important, and this natural enzyme inhibitors are also very important. Okay. So, summing up what we have learned, let us again come back to our starting point, that we started with this Michaelis-Menten kinetics. We talked about the significance of Km. Already we have a discussion in an earlier class about this Michaelis-Menten kinetics. Now, the significance of smallness or largeness of Km is discussed. With the help of Lineweaver-Burke plot, we try to explain various types of inhibition effects. Now, enzyme inhibitors, they are why they are important, because which informations are necessary. Basically we want to get information about the active sites and also the residues that are important in the active sites. We want to get information, or we want to get idea about the mechanism. That is why studies on inhibition is very important. Okay. How metabolic pathways can be affected. Okay. With the help of inhibitors, we can study that, and also most importantly drug design. Okay. Because certain drugs are enzyme inhibitors. That means if we put that drug, or if we administer that drug, then it will bind to the active site of the enzyme, or it will tend to change the local site of your active region of the enzyme by some secondary effect. Maybe it is binding to a distance point from the active site and it changes the activity. So, the study of this enzyme inhibition is very important. Types of inhibition, whether it is reversible or irreversible, we talked about it. Reversible inhibition means it is a non-covalent bond formation, and irreversible inhibition means it is basically a formation of covalent bonds, or rearrangement of a number of covalent bonds within the enzyme, or maybe in the enzyme substrate or enzyme inhibitor complex. Now, competitive inhibition, non-competitive inhibition and uncompetitive inhibition we have talked about. Then the basic kinetic scheme we have given, and three different situations can be obtained out of it. One is for competitive, another is for uncompetitive, and third one is for non-competitive inhibition. We have given the idea of irreversible inhibition, that is irreversibly this enzyme is transformed to something else. Now, different inhibition patterns we talked about. We talked about your in details, taking each situations, like for your competitive inhibition, how it is operative, how this can be minimized, and the Lineweaver bark plot for your competitive inhibition and its characteristics. Then with the help of pictorial diagram we try to explain the competitive inhibition. Then we went to uncompetitive inhibition and the corresponding diagram, Lineweaver bark plot. Then we came to non-competitive inhibition, and with the help of this diagram we try to explain the corresponding Lineweaver bark plot. It is the non-competitive case, how does it look, whether whether we are getting a different Km or not. So, it looks like that we are getting same Km, but different Vmax for your non-competitive case, although for mixed case it is different. You see here this different Km and different Vmax. And the importance of enzyme inhibitors, we try to give you some idea why we need to study, okay. And actually this inhibitor studies are very important for rational drug design. So, this is very important, this is very important means the study of enzyme inhibitors is very important. So, with this words we I would like to conclude this session. So, in the next session we will talk about this kinetics of autocatalytic reaction and oscillatory reactions. So, till then goodbye.